want to ask about exceptional versus superPoincaré algebra as the defining symmetry of maximal supergravity.
Oh, okay. So let me start by thanking the organizers for inviting me. And then, of course, we shall thank David's parents for what they did 75 years and 9 months ago. So that we are here because of you. And it's a great pleasure to be here. I realized that I met David almost 45 years ago. Well, some of you were not even born at that time. And I met him, I'd met John Schwartz 1 hour before, and he introduced me to John. And this was at CERN, in the good old days. And then we have been seeing each other off and on more and more during the years. And I'm very proud because I'm one of these persons that David often gets very upset with. And I take that as a good sign of our friendship. And the last time was a month ago when he was even furious with me. And you can go on doing that. So, you know, David, it reminds me a bit of, you know, you remember this Woody Allen movie, Zelig? You know, this guy was appearing everywhere. So if you go on the internet and you look at advisory boards, committees, it's always there in every, you know, committee you can think of, and we will probably hear more of that. And then, you know, it's of course all over the internet. So if you you Google on the Swedish queen, you know, and you get the picture of her. So, and you know, but we pedestrians, this is the way we see him. We see the back. So we have to be. Sorry?
On the left is the queen.
No, that's the future queen.
Prince.
Crown prince. You know, he's usually in good company. So don't worry about him. I mean, he's managing well in the world. Okay, so much for that, because I have little time. So I'm going to talk about a subject which I've been thinking about for a very long time. The talk is going to be technical. You have to excuse me because I do it the old-fashioned way by calculating. And I'm also going to talk about old-fashioned stuff like Hamiltonians and Lagrangians. And Sasha always tells me that I should not do that, but we'll see. So what I'm going to talk about is something. It's really about n equals 8 supergravity and not so much n equals 4, but I will concentrate on the n equals 8 supergravity. And you know, the interesting thing, well, one interesting thing is that these are extremely complicated theories if you really look at it. If you go back to this Kremer-Julia preprint from 1979, it was 124 pages filled with formula. And you know, you have 128 bosons, 128 fermions. And if you do the wrong thing, you can end up in enormous calculations. Still, if you look at the 4 graviton 1 loop amplitude, it's just this simple box diagram. And this is something that John and Mike and I we computed in 1981. Of course, you have the kinematical factors on the outside. But the whole structure is as simple as it can be. It's really the minimum. So I interpreted it at the time that this looks like a scale, a phi cube theory. And I'm coming back to that. Of course, what we really at that time should be thought of is that, I mean, this must be telling us that there is an enormous amount of symmetry in the theory, which you really get exposed to here. So I want to see these theories as some kind of starting points for doing quantum field theory. I mean, in a sense, they are the minimal what you can get, even though they look very complicated. And I'm not going to believe that they are physical theories, but they are starting points for these the physical theories. And of course, we also want to master these theories since there are low energy limits of the superstring theorem, because in the end we would like to interpret that going over to the superstring. So, in the beginning, you know, of course, the one reason why the paper of Crémer and Julia was so complicated was, you know, they really did it in component form. 128 plus 128. And then, just after, Paul Howe and I, we constructed a superspace formulation. And that was in terms of one superfield. And but it's a 56 under SU8. And you know, it's a function of 8 4-component spinors. And it really has billions of components. There are so many unphysical fields, but they help you to do things covariantly. And so these are the two formulations which have been the starting point for most of what people do in this field. But I had the third formulation also way back in the beginning of the 80s with 2 students. So we studied the theory in the Lycon gauge, where we only keep the physical fields remaining. And then this corresponding superfield, as you will see in a moment, is index-free and has 256 components. And this was, you know, in a sense, when I saw this loop diagram at the time, I was so impressed with that. I thought there must be something, a field with no indices. But in the beginning, I thought it was a scalar. As you will see, this is not scalar, but it's still, as I say, index-free. And the price to do it this way is that we will obtain the theory as an expansion in the coupling constant. And in the beginning, we constructed the 3-point just to see that it existed, and we could see the symmetries in it. Later on, we have constructed higher terms. On the other hand, we didn't do much with it at the time, because these were the times when, you know, we were concentrating on the superstring, and this was sort of a sideline. But coming back to it, it is a lot of interesting stuff in it, I would say. So, of course, one remarkable fact about the theory was that it had this E7 symmetry, which was found by Crémer and Julia. And it works as a sigma model for the scalars and a duality symmetry for the vector fields. And it does not touch the other fields. And of course, this is, you know, comes back as the U duality. And it was a very mysterious symmetry in some sense. And, you know, it was really hard to understand why it was there, I would say. It looked like an accident. Of course, the way it worked was that you have 70 scalars, and you can somehow add in 63, you know, other scalars, and you get 133, and then this is the representation of E7. And the vector fields, you can somehow, there were 28 of them, you can sort of double it to 56, and 56 is the representation of E7. Because, and none of the other fields, of course, look remotely close to be interested in being part of an E7. So, before going, let me also say that this was also found, you know, when you go down to d equals 3, there's this E8, E8 symmetry. And this is sort of a European business. You know, if you go further down, you have E9, E10, 11. All these things started with Bernard Julia in the beginning. You know, he was interested in this row here, at least down to E10, and then people have speculated E11. And there's a huge group of people, including Marc and François, and they have argued that these symmetries might also exist in higher dimensions. That these symmetries should be, you know, more basic to the theories than just occurring in certain dimensions. So, my question has then been, what happens to these exceptional symmetries in the Lycon gauge formulation, where every symmetry is a symmetry between the physical fields? And in order to answer that, I have to give you, now I'm going to be technical, because I have to give you the formulation, at least parts of it, such that you can hopefully understand what I'm going to talk about. So I will describe how to do this supergravity, the four-dimensional one, in the Lycon superspace. So we will use a complexified space-time, you see, and x plus and x minus are the Lycon directions, and we were choosing x plus as the time. You know from Dirac, you know that we can choose any direction within the Lycon to be the evolution parameter, and we choose x plus as the time. Then we introduce 8 thetas and a complex conjugate, and they have an SU8 index on it. That would be the R symmetry. And we also introduce a coordinate so this is the time, and this is the other Lycon directions where we subtract this term. By doing that, we can write the superfield like that. This is, of course, what I was after at the time. And this is a superfield with no indices. I should have written a theta there also. And it starts with the helicity 2, helicity 3/2, goes all the way down to helicity minus 2. And in order to keep track of dimensions, and also because of symmetry reasons, as you will see, we have this, which looks like ugly 1 over del plus. It's a 1 over derivative, which is a non-locality. But if you're unhappy with that, you can Fourier transform it, for example, and then you have to worry about where the pole is. And there are all sorts of prescriptions for that. But on the other hand, if we lived with it for 30 years, it's very easy to work with it. 1 over the derivative. I mean, the main definition is that if you take a derivative of a 1 over derivative, you get back the function. But there are all sorts of, you know, nice, mathematically correct ways of defining it. But that means that we don't have any other parameters. So it only consists of the fields here, with then as an expansion in superspace. And this field satisfies various constraints. One constraint is that we have something like a chiral operator on this superspace that acting at 0. And then for the maximally supersymmetric fields, there is one more condition, which is we write it like that. It looks very complicated. But what this really amounts to is that if you take this field, you take the complex conjugate, and you turn it inside out, then you get it back. You take like a shirt, and then it looks the same. I don't know how to complexify a shirt, but but you know what I mean. So this is the field we are working with. And now, really what this game is about is to find a representation of the Hamiltonian superPoincaré algebra on this superfield. So we have sort of the way we reduced it to completely group theoretic problems. We're going to find a representation of this algebra. So, and then we have to distinguish the various generators. One are the Poincaré generators, the kinematical ones. Those are the ones which do not take you forward in time. And they, you know, they are just like you look at any group theory book on the Lorentz group, Poincaré group, and you have to just remember that I'm using this Lycon coordinates. So this one, this has no index. It's really like a 1, 2, but you know I have complexified. This is the helicity operator. So this guy measures essentially the helicity when we go down the superfield. And yeah, the other ones are, well, they are what they are. So, and then we have one dynamical generator of the Poincaré, that's P minus. And it's a del bar over del plus. So it's, and this will be really the Hamiltonian of the theory. And then we have, well, we have two more. These are the ones in the taking you into the minus direction. They're always complicated. And people who were around, you know, when started doing light-cone gauge in the string theory way back in '72, remember that that's where the juice in string theory comes from. Those generators, if you commute them, it only works in 26 dimensions, for example, for the bosonic string. But then we have supersymmetry generators. I write them like this. I call them plus. And here minus, which again, you know, have this non-locality in it. And the supersymmetry algebra is just divided like that this Q plus is a rather trivial operator. It's a spectrum generating one, and the other one is the Hamiltonian. So in a sense, all the juice in the theory lies in this generator, the dynamical supersymmetry, the one which commutes to the Hamiltonian. And when we turn on interactions, it will get interaction terms, like all the others, dynamical. So that's where the difficulties come. And in fact, if I write the action to the first order, it looks quite simple. You see, there is a complex conjugate which I forgot, but it doesn't really matter. And I said the important generator is this dynamic and supersymmetry. So I get a term like that here. This operator is the other one which had the plus on the. And so we can work with that to first order. We can check, you know, our symmetries, etc., to first order, and we see that things work. We have computed, of course, the next order. That's complicated. It contains some 50 terms or so. But if you do these things in component form, you know, the 4-point couplings in n equals 8 in component form, there are 5,000 terms. That's again one of these things which you see of course that's not the way to do it. But you're using a lot of algebra to describe simple things in a sense. So let me now then turn to this E7 symmetry. Now, of course, the old calculations we did 30 years ago, more than that, but some years ago, Pierre and I, a student of his, Som Kim, wanted to really understand how do we do this E7 on here. And the way, I give you the answer quickly and then I'll tell you how to do it. So E7 we write as we take out the compact, the maximally compact subroot, which is an SU8, and then you have this quotient. And this is, it's trivial, this SU8. And this guy will be non-linearly realized. And I've written the first term here, where I'm using these chiral operators, as I call them. And this is, don't look too much into the form, but it's doable to do that. But in order to get there, that's where we really have to do a long calculation. It's, of course, you might guess it, but we didn't manage to do that. So we have to go back to the original way of doing it. You start with Kremer and Julia, you go to the light-cone gauge, you eliminate the unphysical degrees of freedom, and then not only that, do we have to that, we also have to get rid of time derivatives in the interactions. So that's another field redefinition. So we shuffle around all the fields, and then eventually we could read it off. But the interesting thing is that now you see that these transformations transform all the fields. It's not only the bosonic fields. So I give you two examples. The graviton transforms, and this is the, I guess this means we have field. They all, you know, so one can read off. So the whole super multiplet takes part in these E7 transformations. So you can turn it around and say that the super multiplet is also a representation of E7, which in a sense is surprising. But you know, it's not more if you think about the supersymmetry, I mean, it's also a representation of the superPoincaré, but the superPoincaré group, the way we have represented it here, is nonlinear, and this is also nonlinear. So in that sense, they are on an equal basis. And we can also see that this quotient commutes with supersymmetry, so they don't talk to each other, even though the maximal subgroups does. And it can do that because of the nonlinearity. This is, it looks very, if you do two transformations like that, you get an SUA. And then you might worry about Jacobians, but it does work out. So this is it's true, and so it means that the Hamiltonian is commuting with this here, and that can be used, it's another way of finding the Hamiltonian. So I wanted to stress this, that the exceptional algebra and the maximal supersymmetry are spanned on the same multiplet. And both are non-linearly realized, and both can be used to find the Hamiltonian. So then, in a sense, I would say from our starting point now, these two symmetries are equally important. They play the same role. They are the ones that we use to define the Hamiltonian. So what happens then in 11 dimensions? Well, the nice thing is that we can use the same superfield. This superfield that I wrote you before, this is sort of the conscience in the theory. It's really, carries sort of all the information about the field content. And you can write this field content, in any dimensions from 11 down to whatever. Of course, you have to mix them up differently depending on what, but all the degrees of freedom are there. So the only thing we have to do is that we have augmented with 7 more transverse directions and their derivatives. And now the way we do it is that this is now the new transverse symmetry in 11 dimensions. So we have to divide it up into portions like this, and the SO7, and this is the one we had before. And this SO7 we will use as the R symmetry in the superfield. Because there are 8 component spinor representation of SO7. So we will get various kinds of linearly realized rotations that we can use. So what about now this dynamical supersymmetry? In the beginning, in 4 dimensions, we were only using one of the transverse derivatives. We will now have also the new ones. And this is the one we did not use in 4 dimensions. We didn't need to do it, and there is a reason for that. So it should be linear in these transverse derivatives. And these, so those we have from the old calculations. So what about the new ones? Yeah, so we have to have new terms here with this derivative. And the other guy, well, you see, as I say, terms with that they do not exist in the 4-dimensional formulation. But now, since the R symmetry this time is SO7, then it can allow for that. So had we written the theory instead of using SU8 as the R symmetry in 4-dimensional SO7, then we could have had them. And you have to remember that, in order to find all these beautiful formulations that Crémer and Julia had, they had to do all sorts of field redefinitions. And so from this point of view, we have to understand that those terms could be there. So now we just have to do calculations. Come on. So this is where I'm technical again, but don't look too much at the formula, but just the spirit of it. We can rewrite these things as using some kind of coherent state techniques. We introduce an operator like that, and we take terms linear in this parameter here. We take that out, and then we get an expression which has an alpha dependence. This is a nice way of doing it because this expression is very easy to work with, and we can check all these kinematical symmetries immediately on it. So the thing we now have to do is that we have to look at, but now we have rotations between the old 1 and 2 directions and the new directions. So the dynamical supersymmetries that satisfy this relation. And then we can put sort of an arbitrary ansatz for this. And then we just work these through. And eventually we get an expression like that. We, again, don't look at the details, but you can see that this is quite complicated because this has 5 spinor indices. And if you work it out, if you didn't use its coherent state, I think there would be at least hundreds of terms, if not thousands. But we can all write it in a way like this. And so this is, in a way, our formulation of the 11-dimensional theory which is then manifestly supersymmetric. And then we can compute the Hamiltonian. And we don't need to compute the other dynamical generals because we have seen that the solution is unique, and we know there must be a solution. But then the question is, can we see the 7 here? No, we cannot do that. And the form of this supersymmetry generator is such that we don't see any E7. So does it mean that the theory is not E7 in 11 dimensions? Not necessarily, because we can do something else. So we can try to find a different way of going from 4 dimensions to 11 dimensions. And when we did check these E7 in 4 dimensions, it was very important the way the derivatives work. So if we can copy the derivative structure of 4 dimensions up to 11 dimensions, we will get it, a supersymmetry, no, a Hamiltonian, which is invariant under this E7 up to this order. We're only doing it, of course, to first order, but it's not really enough. So what we have been trying is that we try another way of introducing, instead of, this is the one you have in 4 dimensions. Now we can add in the other ones together with some of these carried derivatives that we have. So we're trying that, and then we try to go through. So we try a 3-point function that looks like this. We check now we check the Poincaré invariance of it. We don't discuss supersymmetry. And we can see we can actually span the full Poincaré covariant. It works. Just get this parameter, 3 parameters, 1. So we're arguing that, well, we have to do some other very technical thing. Now when you look at the superfield, I said that this was, the R symmetry was SU7. But we can always say that it is SU8 because we can span SU8 on the superfield. And SU8 is part of this E7. So we can take the SU8 and the quotient. And to this order, it is E7 invariant. So the Hamiltonian is very different from the previous one. But you know, there is only one theory in 11 dimensions. It must be the same theory. So what I'm claiming is that in this case, there would be a field redefinition from the supersymmetric formulation to the 7 invariant formulation. And in a sense, you know, again, my feeling is that, you know, both of these are equally valid. And they should be used, you know, somehow in conjunction. So let me now go back to 3 dimensions. I said we should also be able to find this E8 invariant in the 3-dimensional formulation. And also in 3 dimensions we can use the same superfield that we have. And I'm not going to too much, but this time we will divide E8. And this SO16, of course, will be the R symmetry in 3 dimensions. And this is the maximal symmetry that we can linearly realize on the superspace we have. So we can do that, and this is so now we will see that all the scalar particles that we have, of course in 3 dimensions we only have scalars and fermions. So all these scalars, of course, participate in this sigma model transformations. And we can form, don't look too much in, but there is a way of doing this again on the superfield. So I only wanted you to look at that. So the supermultiplet in 3 dimensions is also a representation of E8. So you know this supermultiplet knows about E7, it knows about E8. Now we can ask the question, what happens if you go back to 4 dimensions? So we should be able to, I don't like the word oxidize, but that was what people use in this space. We can do it in 2 ways. We can either, you know, you can break the SO16 to SO8 and get back to all formats, and then we see an E7. But the other thing is that we should try to, we can keep the derivative structure, as I said, and then we keep the E8 symmetry. But of course, both should be the same theory. Of course, they will look very differently. And but that would mean, you know, that in 4 dimensions, I'm claiming that there is a hidden E8 symmetry also. And that might explain so I would say, you know, all these counterterm arguments that people have been using is based on the superfield, that this covariant superfield that we, you know, which somehow is on which you can represent the E7, but we cannot do E8. So what I'm saying is that I think we should expect better quantum behavior in 4 dimensions than what the standard counterterm arguments would give. Because this is what Sviburn and these people see. I mean, he has always bets with Callistelli about what's happening, and he's winning every time. And I'm telling him that he should keep on betting with him. And he can give me part of the bottle. I guess he doesn't even drink wine, I guess. See, but that's my... So what I'm... of course, people in Europe, I would say, have been wanting to have that this theory should be... even of course, Svi is also convinced that n equals 8 supergravity is a finite theory. So my question, what does it say about quantum finiteness? We don't know. I mean, I'm only claiming that things are better than what it looks like. And of course, this makes it rather tough because I would claim, you know, that we cannot settle this unless we can do explicit calculations, because I'm not sure that we have discovered all the symmetries that there are in these theories. There could be even more, you know, very complicated symmetries lurking around here. So it's yep. In principle, you can do it, yeah. But you know, I've been thinking about it, and I even set up the formulas for doing it. But it's too hard for me. I'm alone, you know. I know. You mean the 7 loop arguments that people have, or? Yeah. That the theory should be invariant under at the quantum level. No, that's a hope. But there are strong arguments that D7 is not anomalous, and in that, I think that the same would be true for E8. But I don't know, of course. This is very tough problems. So, as I said, I've been trying for years, to set up this counterterm. I mean, I have to do better than what the other people are doing, and it's technically too difficult for me. So we don't know. But as I say, of course, is it possible? We know that Seaburn and Lance Dixon and their collaborators, they computed the for loop, and that amounts to evaluating 10 to the 26 Feynman diagrams if you happen to do it with Feynman diagrams. And 7 loops, I don't know. I saw big numbers. You can. On the other hand, I think they had 50 or so different terms to consider. So that doesn't seem to be the right way either. I don't think we will solve this problem. On the other hand, I think what we can learn, again, what I'm saying is that, I mean, I can do this calculation because I'm old enough. I don't need to. I cannot even compete about grants any longer. I'm not eligible to that this evening, so I can do at my own pace. And I want to, beat these theories down to we really understand that there are so much symmetry, and of course, at some stage, we should take that over to see what does it mean for the string. And this is what also I would like to do. And I hope to do. So I think this is probably my last slide. So, as I said, it can very well be at the tip of the iceberg, because all these arguments that Francois, Martin, and Hermann Nicola, and the rest, I mean, they've seen signs of these even bigger symmetry of Kac-Moody type, and I don't know how to do it here. So it is intriguing. I think we're working on a structure which contains so much underneath it, that we have to just dig and dig. As I say, I think it can have consequences for the thing. Perhaps we should, when we have constructed string theories, we've always been looking at the supersymmetry. Perhaps at some stage we should also look at these exceptional symmetries and see if they can help us, forgetting about the supersymmetry for a moment. So my message is that these theories are probably in a sense, the ultimate of quantum field theories, the basic of quantum field theories, and somehow we have to learn to work from that level upwards to get to the physical theories. Okay. Thank you. Mm. No, we have the second order, not for this, but yeah, for the E7. Then the next order is kappa cubed there, because it goes every order, and it is my faith is because I've been living in this world for so long, and things have worked out. I've never seen any problem with that. And then at some of these problems you can translate to other problems in the covariant formulation, and you see that it works. But I mean, I have to be honest, we haven't really proven anything more than up to a certain level that it works. So it can very well fail. No, I think that if you do the counterterm argument, you see one problem. If you want, you can somehow write down, for example, a 4-point term, counterterm. You will have, I don't know, 15, 20 derivatives or something. And then, so that's a new term. That, in order to check the E7 invariance for that, then you have to go one term up again, you know, because these nonlinear sigma terms work, you know, jumped 2 at a time. And this is one of the reasons why it's so difficult to of course, if you could, yeah, I know things become too difficult. It's, but you know, since we are young, we can hope that we can. Oh.
Mm-hmm. To get to having these symmetries having a larger meaning than what you think they are. So, according to that mesh too. And but I think we should not forget that these are functions of duality. They came as duality symmetry, which the constructive part will raise for. And think that we are going to be able to enlarge this to a kind of symmetry where the compactification goes out. It certainly is an interesting dream, and you always find some indication that maybe it works in always the EU or the after the given level of symmetry. And so that's my impression is that this is very nice to read. But really, it's kind of a miracle if it were that it would happen. Now I don't believe in miracles in this sense.
No, but let me say,
see why it should work.
I think the difference here that at least we have this very systematic way of checking things, going order by order. Because technically it's impossible. Perhaps one can, I don't know, with mathematical sample one can go further up and one can, I mean, if one had an army of people, one could really try to do it, you know, push it up a few orders. So in a sense it's a dream, but you know, I think one should take the dream seriously and somehow work on the assumption that it's true, because then perhaps you will be able to understand other things from that. It gives you some kind of confidence, you know, that there are these huge symmetries, that the huge symmetries are possible in these theories, and that they might explain why these things work so much better than you would expect it to work. Oh, you have David. Yeah. No, I'm not. You know, I like string theory. I like string theory to be the finite theory, but I mean, I've hung up on this. I don't know what's happening here. I should be honest. But it's remarkable that it's, you know, finite up to. And first of all, it's only a perturbation theory. For the other thing is that remarkable that it is finite. So of course you might say that it's because of the huge supersymmetry, but I don't think that can explain all of it.